So now we can start thinking about different modes of inhibition or control of enzymes. And so let's say we have an enzyme which we'll call E, and then we have its substrate which fits very nicely into the active site of the enzyme. So that's shown here in blue, which we'll call S for substrate. But then we have another molecule that also has just a similar enough shape that it can compete for this same active site. And so this may not have any chemistry at all. This may not be able to be converted by the enzyme, but it may be able to take the place of the substrate and inhibit substrate from binding to this so that the normal function can occur. So this is called competitive inhibition. And so this arises when two molecules, one of which is the substrate and the other is not, can compete for the exact same binding site of the enzyme. And so the effect of this is, what this looks like is if we have an enzyme substrate reaction, and for instance if we're following just a simple Michaelis-Menten mechanism like this, E plus P, we can also have an alternate pathway where instead of substrate binding, the inhibitor binds. We'll color code this. So instead, inhibitor binds to the enzyme, displacing substrate, and instead you get this enzyme inhibitor complex. There we go. Where the inhibitor may bind very tightly to the enzyme and therefore not leave any free enzyme around so that the substrate can bind and so that this chemistry can continue. So what you might expect for this is if we're looking at Lineweaver-Burke plots, okay, so if this is wild type enzyme without any inhibitor, so we'll call this no inhibitor. This is going to have, again, if we remember our Lineweaver-Burke plot, we're going to have a slope which is equal to Km over Vmax, and we're going to have B, or the y-intercept, that's going to be equal to 1 over Vmax. So for a competitive inhibitor, this is displacing the ability of the substrate to bind, but it doesn't actually change anything about, for instance, the rate constants of the enzyme. It just gets in the way, so it impedes the ability of substrate to get in there. So what that effectively does is that increases the apparent Km. So Km can be thought of as sort of as an affinity. So if there's an inhibitor in the way, this decreases the infinity, which means it increases the Km. And so what you would expect is as inhibitor concentration goes up, let's say this is 10 micromolar, 0 micromolar inhibitor, 10 micromolar inhibitor, and 100 micromolar inhibitor. So what would happen is in your Lineweaver-Burke plot, these would all converge at a single y-intercept, which again is 1 over Vmax. So what that implies is that Vmax is not changing in the presence of the inhibitor. But what is changing is the slope of all these. So Vmax we know is not changing, so that must mean that the Km is changing. So as the concentration of the inhibitor goes up, the slope is increasing, meaning the Km is increasing. And remember, Km takes units like a dissociation constant. So this is in terms of, in some unit of molarity or micromolar or millimolar, depending on how you define it. And so as the Km increases, what that means is this Km increases, which means that the affinity of the enzyme for substrate is decreasing. And so that's the effect of competitive inhibition. By blocking the active site for its normal binding to substrate, it is in fact decreasing the affinity of the enzyme for the substrate.